Today we're going to talk about linear approximations and differentials. They're very related to each other. First of all, let's deal with linear approximations. First of all, what is a linear approximation? Very much as it sounds. Linear meaning straight line, and approximation, we're approximating a more complicated curve like y equals f of x, but we're going to approximate it with a much simpler straight line. And at first thought, you're thinking there's no way you can come up with any straight line that's going to approximate a complicated curve like that, and you're very right. But if we're only concerned in a certain area, like say really close to some point A, x equals A. So then maybe we can find a line. We wouldn't want to use this line down here, but maybe if we drew a line that has the same slope of the curve at that point, that's going to be the best approximation we can do. And I think if you look at it, if you cover up that brown complicated curve except for a little area right around that dot, it almost looks like a straight line. So you can get a good approximation. Now, if we need an equation of that straight line, we need a point A, comma, f of A, and a slope. Well, now we know that the slope at that point is going to be f prime of A. So we could write the equation y minus f of A equals the slope f prime of A times x minus A. And just solving for y, and let's call it the new function of x. So we could call y L of x. And if I just bring the f of A to the other side, this is the formula for a linear approximation. We're starting out with y equals f of x, a more complicated curve, and this would be a new function, L of x. That would be a straight line that approximates that curve really closely right in the vicinity of x equals A. Now, if you really like, you can memorize that, but I think we've already done this before. This isn't really new. What is this line? We've been calling it the tangent line, and we've done examples of finding the tangent line. So really, this is just another name for something that we already know. A tangent line is also a linear approximation for a curve. But it kind of shows you what a tangent line can be used for. It can be used to approximate more complicated functions. And that's kind of what we're going to talk about at the beginning of today. So say you wanted to estimate the cube root of 8.1 and you didn't have a calculator. Well, what you could do is say the function that I would like to use to approximate the cube root of 8.1 would be y equals the cube root of x. And we know that that function looks a little like that. The cube root of 8 is 2. But the trouble is, even though we got the function, we can't just put 8.1 into it because we can't do that calculation in our head. So what we're going to do instead is we're going to take a linear approximation for this function. We're going to find basically a tangent line. So what do we need? We need a point, which we've got, because we can easily take the cube root of 8, and that's really close to 8.1. And what we're going to do is be finding this tangent line. And you can see, because this is a fairly flat curve, that that tangent line should do a pretty good job of approximating at 8.1. Because what we're going to do is go over to 8.1 and see what the tangent line says. From the graph, it looks like our approximation is going to be a little bit too low. Well, we'll see how it turns out. So, we could use this formula, but basically we can just say, like we've always found the tangent line. We can say y minus the y value equals the slope times x minus the x value. Well, we still do have to figure out what the slope is in order to get something to put in here. So, do we know how to take the cube root derivative? Yeah, this is really just x to the 1/3. So the derivative is 1/3 x to the negative 2/3. We use the power formula. The derivative of x to the 1/3 is nx to the n minus 1. And it can be written a little bit nicer without negative exponents, like that. And now we can plug in x equals 8. Well, 8 to the 2/3 power, the cube root of 8 squared is 4. So this just comes out to be 1/12. So we've got a tangent line, a linear approximation. And now all we have to do, we can say that our y value is approximately equal to, we just move the 2 to the other side, and we plug in 8.1 for x. Now, still a little bit of calculation, but what do we know? 1/12 is 0.083, and we're multiplying it by 1/10. So it's 0.0083. This is what we get as an approximation to the cube root of 8.1. Now, if you go to your calculator, what you're going to find out is it's 2.00829. As we kind of expected, we did a really good job. So, I think we had a pretty good first try with linear approximations. Now, maybe something even more valuable than that. Oftentimes in physics and in engineering, we have a fairly complicated function, but used a lot is the sine of x. So the sine of x, if you were to graph it, is going to be something that looks like this. So that's what the sine of x looks like. Now, obviously, there's no straight line that's going to do a great job of approximating that. But often in physics and engineering, you're looking to use the sine of x, but you know the angles are going to be quite small. So we're really only looking for an approximation near where x equals 0. Well, one thing you could do is say, let's find a tangent line. Something to approximate that, and we have a point, 0, comma, the sine of 0, and we can get the slope fairly easy. The derivative of the sine we have proven to be the cosine of x. And if we plug in 0 to that, the cosine of 0 is 1. Well, we certainly don't need a really fancy equation like that. We know if it goes through the origin with a slope of 1, it's just the function y equals x. So what have we found out? We found out that if you're only looking near the origin, that you really can't see much difference between y equals the sine of x and y equals x. The tangent line looks almost identical to the curve. It's a good approximation. And in their calculations, it's often really nice to be able to replace the sine of x with just the expression x. And it makes everything work out nicer, and the error is very small, something that they can deal with as long as they know there's an error there. Just to give you an idea, if you take the sine of 0.1 radian, it turns out to be, and I looked this up on the calculator, 0.0998. Whereas, what would we say? We would say the sine of 0.1 is really just about the same thing as 0.1. That would be the approximation. And you can see it's extremely close. And you could say, well, 0.1 is such a small angle, but we're talking 0.1 radians, which is almost 6 degrees. So we can go 6 degrees, we can go up to angles of 6 degrees, positive or negative, and still have a very accurate representation by calling the sine of x just x. So that takes care of linear approximations and some of their use. Now we're going to go to differentials. Well, differentials are very associated with linear approximations. If I were to start at some point x and move to another point where I change the value of x by a certain amount, so that I'm going over here to x plus some change in x, what I see is I get a change in y. So I have a change in x, which gives me an associated change in y. But it's often a little bit hard to figure out exactly what that change in y is. So what we could do is take a linear approximation at this point x. We could draw in a tangent line. And then what we see is this little distance from here to here, which isn't exactly the change in y, is an approximation for the change in y. So from here to here is the actual change in y. We're going to approximate it by this little distance, and we're going to call it dy, the differential of y. And just so we can make x happy, we're going to call the change in x the differential of x. It's really the same thing as the change in x, whereas the actual change in y and the differential of y are different. Well, what we're going to do is we're going to use this linear approximation to approximate the change in y. Well, how can we do that? How can we come up with a formula to figure out what dy is? Well, if you look at this blue line, what's its slope? Its slope is f prime of x. And also, if you forget about the derivatives for a minute, just look at the rise over the run. If you look at this triangle, the slope of this blue line is the dy over dx. So with just multiplying both sides by dx, we see that dy, the differential of y, is the derivative of f at x times the differential of x. So that's the derivation of the formula for how you find the differential of y. And you can kind of see that we're dealing with Leibniz notation. Leibniz could kind of see this in his head when he came up with that notation. He thought of dy as being an infinitesimal change in y, and dx as an infinitesimal change in x. So he could see this slope at that point just being a small change in y divided by a small change in x. And that's why I think he used that notation. So, how can we use this? We could use it just on a regular function, like y equals x squared, but I thought I'd give you some more practical uses than just looking at specific functions. Let's look in real life for how you could use differentials to help you. So coming over here, after having an ice cube in your mouth for 5 minutes, the edges of the cube changed from being 2 meters to 1.9 meters. Okay, so you have a pretty big mouth. What we want to do is estimate the decrease in the volume of that ice cube. Now, obviously these days we've got calculators and it wouldn't be too hard to get the volumes at both places and then subtract, but there's going to be good reason for understanding how to do this even though we have calculators. So if you take an ice cube, the only really variable in that, the only independent variable would be the edge. So say the length of the edge is x. And what are we talking about? We're talking about the dependent variable being volume. Well, do we know the relationship between the volume and the edge of a cube? I think we do. We can just say the volume is x cubed. So going back to our definition of differential, that dy was equal to f prime of x dx, that's when x was the independent variable and y was the dependent variable. So the only difference now is v is the dependent variable instead of y. So we could say dv equals v prime of x dx. And we know what v prime of x is. It's the derivative of x cubed, it is 3x squared. So now we can just plug in what we know. For this particular problem, x starts out to be 2 meters. So that's the original x. And dx, the change is 0.1. It's actually a negative 0.1, but we're only looking for the change, so I could just leave it as 0.1 for now. And what do you get? 12 times 0.1 is 1.2, and it would be in cubic meters. Now, if you actually go to a calculator and plug that in, it comes out to be 1.14. So again, we're very, very close. Sometimes, better than having an actual estimate of the actual decrease, we want an estimate of the percent decrease. Sometimes it's better to look at percentages. So what would be an estimate? The actual would be the change in volume over the original volume, but an estimate is going to be this differential of volume, an estimate of the change in volume over the original volume. And at first thought, you're looking, this is going to be a more complicated calculation. But if you look at it, dv is 3x squared dx, and v is x cubed. So if we just do some canceling, we get 3 dx, which is a negative 0.1, but we're just looking at the change, so we could say 0.1, over the original x, which is 2. Well, 3 divided by 2 is 1.5, so this is 0.15, or 15%. And the calculator, if you actually did this, actual comes out to be 14.3%. So again, without much work, we came up with an estimate that was very close to the actual. Okay, so let's go from having ice cubes in your mouth to be somebody who's exploring the surface area of Mars. So we kind of know from our measurements that Mars is approximately a sphere with a radius of 1,531 miles plus or minus 0.1 miles. So whenever you're measuring your instrument that you're using, or whatever method you're using, there's always some tolerance where you're off by a little bit. So we want to, this isn't like we really have a change. Radius of Mars isn't changing, but there's an amount that it's off by. That's, you can think of that as the same thing as a change. So what are our variables here? Well, our independent variable is going to be the radius. The dependent variable, because we're interested in the surface area, we could call it A. And if we remember our geometry, the surface area is 4 pi r squared. And what we're trying to do is we're trying to estimate the effect of this change. So there's going to be a change dr of 0.1, and we want to know what the change in A is going to be. An estimate of the change in A is just dA. Well, it's the same formula, but instead of F, we now have A. Instead of X, we now have R. So the differential would say A prime of R dr. And we know the derivative of A. It's 4 pi times 2r, or 8 pi r dr. And we can do that calculation. 8 pi r is 1531, and dr is plus or minus 0.1. And just to save you some time, I put this on a calculator and got 3,847, and it's surface area, so it's going to be square miles. And you're going to say, is that something I can deal with, that off by that much, if I'm a scientist and studying Mars and its surface area? Well, sometimes, as I said, a percentage calculation would be better. So instead of finding an estimate of the actual change in the surface area, let's estimate a percentage change, just like we did up here. So now what is it going to be? dA over A. Well, we've already done dA. It's 8 pi r dr, and A is 4 pi r squared. And often in these calculations, you get quite a bit of, you can get rid of a lot of things by just canceling. Pi cancels with pi. 8 divided by 4 is 2. This r cancels with one of these r's, and you're left with what? 2 dr over r. Well, dr was 0.1, and r was 1531. And if you put that on the calculator, you get 0.00013. And in a percentage, You just move the decimal places 2 places and you get 0.013%. So only about 1/100th of 1%. Maybe that's something that you could deal with. Okay, so let's go from looking at Mars to being a doctor. And you've got a patient who's having a little bit of trouble with their blood flow. So it happens to be known through scientific research that the volume of blood flowing through our arteries of radius r is directly proportional to the 4th power of the radius. Well, that's enough to give an equation, a function. The volume, it's not equal to the 4th power of the radius, it's directly proportional to. So you have a proportionality constant. So everybody has this relationship, but different people have different values of k. But it's still, we're going to find out that the k turns out to not be very important in this calculation. So what do we want to do? Well, we don't have anything in this problem about an actual amount change in r. What we do know is the radius is going to be increased by 10%. So that's not dr, that's a percent change in the radius. So we know that that's dr over r. That's equal to 10%. You could either write it as a percent or you could write it as a decimal. Doesn't really matter whether you want to work in one form or the other. But we're really looking for what? The change in the volume. We want to know, can we give this person more volume if we increase the radius? Because it's going to take a little bit of risk to do this operation. But if we can do it and get a big increase in the volume of blood, it's going to make this person feel a whole lot better. So, since we don't have actual numbers, we're not going to actually be able to find dV, the actual change, but we can find dV over V. So let's try to find dV over V. Well, V we already know is kr to the 4th. What's dV? Using our good old formula here, it's going to be V prime of r dr. And this isn't too hard to take the derivative of. The k is just a constant, so you get 4kr cubed dr. So I can put that here, 4kr cubed dr, and sure enough, we get some good cancellation. The k's cancel, almost all of the r's cancel, and you're left with what? 4 times dr over r. Well, we know that's 10%. Well, 4 times 10% is 40%. So if we can do an operation to increase the arteries by 10%, the radius of them, we can increase the blood flow by 40%. And that person is going to be feeling a whole lot better and a lot healthier. So anyway, I hope that shows you what differentials can do to help us and linear approximations. So that finishes up the chapter on derivatives. That doesn't mean we're done with derivatives. The whole next chapter is on applications of the derivatives. But as far as actually what derivatives are and different types of formulas, we've covered everything in this chapter. And then maybe in 2 or 3 chapters down, we'll get into some other functions that we have to still find the derivatives for. But we've made quite a bit of progress to this point. So have a good day, and I'll hopefully see you the next time.